Hello and welcome to the MOOC on optical communications. In this module we will discuss power spectral density of the pulse shapes, that is a continuation of the previous module where we had discussed the type of pulses that are normally used, especially when you talk about baseband communications. Of course, we are not going to really do baseband communication here with optics, fiber optics, but it is necessary to know what would be the pulse shape that would have, because it would have an impact on the bandwidth and hence the performance of the system. So, we have already seen that we have different pulse formats available or the line codes that are available. The popular ones are the polar format, right, and then you have the unipolar format, and we have also discussed bipolar format. Okay. If you are concerned with pulse shaping at the optics level, then you are pretty much going to use a unipolar format, because if we are concerned with the pulses in the optical domain, then you are pretty much going to use the unipolar format, because in the polar format or in the bipolar format the optical power or the amplitude, signal amplitude could be positive or negative. While that is still true in the optical domain, if you are looking at intensity modulation as one of the modulation that you are looking at, then you can't really have an optical power which is negative. So, you end up almost using a unipolar format, and if you were to try and use different pulse shapes that we had talked about in one of the earlier modules, right. So, we had talked about in the earlier modules about 67% duty cycle pulse, the 33% pulse shape or a 50% pulse shape. These pulse shapes in the optical domain will have a certain bandwidth in the optical domain again, and the available bandwidth versus the bandwidth occupied by the pulse has to be adjusted appropriately. So, if the bandwidth available is fixed, then you have to choose between different pulse shapes in order to be within the bandwidth that is allocated to us. However, the electrical signal that comes and modulates the optical carrier. So, you have an optical carrier such as emitted by a laser, which then goes into an external modulator, right. This external modulator has another input in the form of the RF or the voltage signals, RF voltage signals. These RF voltage signals will also have to be encoded in an appropriate way, because what happens is this RF voltage which is carrying the information is pulse shaped, okay, changes the optical carrier which is now modulated moves through the fiber. At the receiver you receive the optical field, and once you have received the optical field you put a photodetector, and get the electrical waveform back. So, if this optical carrier is simply carrying the electrical data to us, if you look from the electrical data point of view, you take the electrical data, pulse format it, put it into the optical carrier and recover the electrical waveform back here. So, from the electrical data point of view, if you are looking at it, you can think of this as an equivalent electrical system. Okay. The optical part can be dissociated with this. And here again, in order to perform a proper electrical reception of the signal, you have the voltage waveform that you have received which is carrying data. Typically what you do is you put a match filter. So, if you want to put a match filter, you have to know what is a pulse shape. Again, the pulse shape in the electrical domain will have an impact on the bandwidth, will have an impact on the performance of the system. So, it is necessary to pulse shape both in the electrical domain and in the optical domain. Sometimes you do not do pulse shaping in the optical domain, that is something that you do when you are modulating the phase of the optical carrier. There you try to keep the envelope of the optical carrier constant. However, the earlier generation optical communication systems utilized intensity modulation or on-off keying digital modulation, wherein the intensity of the optical carrier was changed. So, in the digital communication case, we were sending a sequence of optical pulses. If the pulse was present, it would represent a bit 1, and if there was no pulse, it would represent a bit 0. Right. So, these are different reasons why we pulse shape, and that is necessary, that why we are studying this pulse shape. So, with that in mind, let us look at the power spectral density of the pulse shapes. What is this power spectral density? We know what is power, right. If you consider a simple sinusoidal signal and imagine that simple sinusoidal signal is actually being generated by an ideal voltage source, you give that across a resistor, then there is an average power that is associated with that sinusoidal signal, correct. If you, the instantaneous power of course will be V square by R, and if you consider for mathematical simplicity R equal to 1 ohm kind of normalization, then this normalized power that you are looking at will be, the normalized instantaneous power will be V square, right, if V is the voltage of a sinusoidal waveform. And if you look at the average power, because that is what you are interested in, the resistor actually dissipates this average power. So, if you are looking for the average power, then you have to average the result. But associated with a pure sinusoidal signal, there is a non-zero average power. Now, if I change the frequency over here, right, and the amplitude of the sinusoidal signal, the average power will also change, okay, but because the amplitude has changed. If you keep the same amplitude, it will be the same power. However, this power is now associated with this frequency, right. So, what power spectral density will tell you is what is the distribution of the power, how is the power or the average power to be sure. So, what is the average power, how is it distributed across different frequencies. Okay. You can imagine that you generate a voltage waveform, okay, V of t corresponding to a frequency f0, then corresponding to frequency f1, f2 and so on. Of course, there are an infinite number of such frequencies, and corresponding to each frequency you are going to plot the power. Okay. If you see the power spectral density going something like this, this actually tells you the average power associated with the f0 component is so much, the average power associated with f1 component is this, average power associated with f2 is this one. Of course, because there are an infinite number of frequencies and it is better to work in the continuous domain, in fact power spectral density is usually a continuous quantity which tells you how the power is distributed. So, for example, this is called as a two-sided power spectral density, PSD is the short form for that, and of course power spectral density is a function of frequency f. Okay. So, this is the 0 frequency, and you can see here that the power spectral density is more or less uniform, which is a characteristic of a real autocorrelation. We will not get into that detail here. So, if you want to look at how much power is actually being associated with a band of frequencies which is centered at f0, and let us say this is the band that I have. Okay. So, this is the band that I am looking at. So, in that band the power that is associated will be obtained by looking at the bandwidth which is delta f, around f0, and the value of this power spectral density here may be PSD of f0. So, the power that is associated with the band of frequencies delta f is obtained by looking at the power spectral density at the center frequency multiplied by delta f. Because this is a two-sided power spectral density, you also have to consider an equivalent power or in equal amount of power in the negative frequency side. So, you usually end up having a 2 times PSD of f0 times delta f. In fact, when we talked about noise, we wrote some spectral density formulas, right. So, we said the noise associated with a load resistor RL is given or has a power spectral density of 4 kT by RL. And if you then consider a particular band of frequencies which had a bandwidth of B centered at some f0, in this case the power spectral density is flat, it does not depend on f0. So, this is the same value, but you multiply this one by 2B, you are going to get the total power inside your bandwidth. Okay. So, this is the usefulness of power spectral density, it tells you how the power is distributed across the frequency band. Okay. Because you are looking at frequencies around 0, this is the baseband signal or the power spectral density of a baseband signal, hence it is two-sided. You can also have a one-sided power spectral density. For example, noise waveform having a one-sided power spectral density is given by N0, okay, as a function of frequency. Then if you consider a filter, okay, whose bandwidth is B, right, then the total noise in this bandwidth is given by N0 into B. Okay. So, this is the power spectral density, and it is usually measured in volt square per hertz in the typical noise phenomenon, or you can measure this one as watts per hertz, okay, because N0B has to turn out to be in watt. So, you can measure the power spectral density in watts per hertz. Okay. So, this is about the idea of power spectral density. Now, let us jump right into finding the PSD of some of these waveforms that we are looking at. We will be particularly interested in polar and unipolar formats. Other formats which are important will not be covered in this course, but they will appear in the exercises. So, you will get a chance to look at the power spectral density of those formats as well. So, let us begin by looking at PSD of a general waveform. Okay. That is, we have not yet defined PSD, we have only given you the intuition behind PSD. We are going to define PSD now. We imagine that we have a source, remember this source is putting out bits, at the nth time it generates a bit Bn. Okay. Since we are going to use binary lang case, this Bn sequence will be 0 or 1. Of course, the modulation format or the line coding will change this. What does the line coding do? Bit 0 will be represented by -1, bit 1 will be represented by +1. What format is this? This is the polar format, correct. So, in the polar format we replace the symbols by numerical values, and this is the mapping that we are going to do. If we are looking at unipolar format, a 0 will be represented by number 0 and a 1 will be represented by a number 1. Okay. So, this is your unipolar format. But this is not just what is happening. I have given in the previous module, we have talked about how these bits Bn are generated, from non-data, non-electrical data, electrical data, and all that process we have looked at. But the sources cannot, you can't just communicate numbers. I can't take an optical fiber and say +1, nothing. The optical fiber will not do anything, right, because it can't recognize a number. So, we have to convert this into waveforms, right. And this is where we talked about NRZ type of waveform, RZ type of waveform, right. So, if my modulation format happens to be NRZ but polar format, if I have a sequence 101, then the waveform that would look like, assuming that this is a rectangular waveform, that would look something like this, correct. So, this is my waveform. Here you can identify the basic pulse shape. The basic pulse shape that I am using is a rectangular pulse shape. What is the duration of the rectangular pulse shape? TB seconds. Okay. At each TB second, I take the rectangular pulse shape, multiply it by the appropriate bit. If the bit value is +1, I generate a positive rectangular pulse of maybe amplitude 1 and then send it out. Okay. If the bit happens to be 0, then I have to invert this pulse because 0 is represented by -1. So, that is the net result. I take -1 and multiply it to a positive rectangular pulse, I get a minus or a negative amplitude pulse and I send it out as it is. Okay. So, that is what I am essentially going to do. So, if I am sending a sequence of such pulses and I do not know what is beforehand, which bit is going to appear, right, because the bit sequence, if I know, then there is nothing to communicate. So, in a sense you want randomness in the system, and you get the randomness in the form of not knowing which bit comes next. We have also said something else. We have said that it is possible that the bit Bn at the nth time might influence bit at n plus 1, bit at n plus 2, and let us say bit at n plus L, if I am considering a word of L letters. Okay. If I have word of L letters, then it is possible that this Bn might tell you or might be influencing all this. As I said, a proper representation of this is to assume that you are looking at a source with memory. Source with memory is called as Markov source modeling. Okay. A simple modeling, on the other hand, would tell you that the occurrence of Bn is independent than the occurrence of Bn plus 1. It is also independent of Bn minus 1, and in fact each bit that appears will be completely independent. This in turn generates a sequence of random numbers, okay, or random bits. The distribution of each bit will be according to a certain probability distribution function. Okay. So, this sequence, which consists of a sequence or the entire sequence, which is nothing but a sequence of random numbers distributed equally, identically distributed but occurring independently, is called as a IID sequence. An IID sequence tells you that it is independent and identically distributed sequence. We are going to assume an IIT sequence. Okay. So, we will assume that this sequence Bn keeps being generated every TB seconds, and you are going to multiply this Bn with an appropriate pulse. If the pulse at 0 time, some origin of reference that we are going to consider will be lasting from 0 to TB, right. Pulse in time duration 1 or the time slot 1 will be from TB to 2 TB. Then you have 3 TB to 4 TB, 4 TB to 5 TB and so on. So, you just give an appropriate number. It's kind of think of this as a train having these bogies, right. So, each bogie will be represented by a number -1, 0, 1, 2 and so on. You can even think of the bogie shape as the pulse waveform, right. So, if I am looking at the nth bogie or the nth time slot, I am down here and I am looking at n-1 TB to n TB, that is the duration, right. So, if it is a third pulse I am sending, it should last between 2 TB to 3 TB. That's essentially what I am doing, and mathematically you can represent this train of pulses, as we call them. The train of pulses can be represented by multiplying the pulse that occurs at nth time slot, which is given by P of t minus n TB. From your signals course, you might know that if this is a basic pulse shape, so let us call this as time t, and let us say this is some TB by 2, this is minus TB by 2. Here I am showing you a rectangular pulse. If you are fancy enough, you can actually have this pulse, right, it does not matter, but the duration of the pulse has to be within 1 TB units. Okay. Then what, so if this is P of t, what would be P of t minus TB? This would be shifted in time by TB seconds, right. So, the pulse would actually look like, so in the duration of minus TB to plus TB2 there is nothing, but from TB onwards you actually get this pulse, right. So, this is TB from TB by 2 to 3 TB by 2. Okay. So, this corresponds to pulse which has been shifted by one time duration. Okay. Similarly, you can think of the nth time and you call this as some S of t, this would be the transmitted signal. Of course, first let us consider a finite duration train, okay, train of pulses going from n equal to minus n to plus n. There is nothing specific about minus n to plus n, you can take it 0 to n, does not matter, 0 to n minus 1 does not matter. So, here is what I am considering. Of course, what I want is not just this finite sequence of pulses, because you assume that communication has been happening from time t equal to minus infinity to, and it will go on up to t equal to plus infinity. To obtain that, I take the limit n to infinity, right. So, I keep adding more and more number of pulses into this. This is your signal that is being transmitted. Okay. Now, the power spectral density is defined as the Fourier transform of this time limited signal, okay, the magnitude square of the Fourier transform, which is then averaged and divided by the total duration of the pulse train, okay, and you let this total duration go to infinity. Okay. Here, if P of t is the basic pulse shape, from Fourier transform theory we know that the pulse P of t has a Fourier transform of P of f. Okay. So, let us substitute that into this. We also know that the Fourier transform of P of t minus n TB will be in the Fourier domain, that would be P of f. It is a pulse that is shifted in time, therefore, in frequency it gets multiplied. So, you have e power minus j 2 pi f n TB. Okay. So, let us substitute these values into the expression and then see what we are going to get. So, I have S of t here, the Fourier transform of S of t is S of f, and I can obtain the Fourier transform. So, if I have to do the Fourier transform, I take the Fourier operation over here to the entire pulse. Then I interchange the limits of Fourier and f, okay, and I go to the Fourier transform. Bn is a sequence that does not have a Fourier transform, whereas the Fourier transform of this P of t minus ntb is precisely this fellow. So, if I take the Fourier transform, what I get is S of f is equal to P of f, and this does not depend on the time slot. So, I can just pull it out. You have the limit n going to infinity, summation n going from minus n to plus n, you have Bn, and then you have e to the power minus j 2 pi Fn Tb. This is the Fourier transform, but we do not want the Fourier transform. What we want is magnitude of Fourier transform square. Magnitude of Fourier transform square is actually S of f into S complex conjugate of f. Okay. So, what is S complex conjugate of f? You take this equation and conjugate the complex numbers. Okay. P of f might be a complex number corresponding to a given value of f. This is a Fourier transform which is complex. So, P of f becomes P complex conjugate of f. The bit sequence Bn is not really complex, it is a real number that we have chosen, but for notational consistency let us put a conjugate there also to remind ourselves that this is a conjugate that is coming from. And when you take the conjugate of this fellow, minus becomes a plus sign. Only thing is, while you can take the conjugate, here you have a variable n. Okay. When you have a summation like this, if you want to take the square, you have to actually put one more summation, right, because this is sum of like, it is like a plus b and you want to take the square of that. So, you can obtain that by writing a plus b, then multiplying it by a plus b. Okay. So, you get a square plus ab plus ba plus 2 b square. So, that is the actual way of writing it, right. So, you can write a plus b square as a plus b and a plus b. Okay. This is square, this is not magnitude square, therefore, you just wrote the same thing twice, and this can be written as sum ai, I equals 1 to 2, and this can be written as aj, j equals 1 to 2. Okay. So, using the same ideas, we are going to write down the S of f mod square and then put the averaging operator. Okay. So, this S of f square will be equal to P of f magnitude square. Why is P of f magnitude square? Well, you are going to get P complex conjugate of f there, right. So, this would be that, and then you have limit of n going to infinity, you have n equals minus n to plus n, right. You have Bn e power minus j 2 pi Fn Tb. You also have some m equal to minus n to plus n, you have Bm, right, e to the power plus j 2 pi Bm complex conjugate plus j 2 pi Fm Tb. You can then rearrange these summations. Okay. So, this would be as it is, the limit would also remain, the summation here can be pulled to the left. So, I am going to use a shorter concise notation, I say summation of n and m, okay, and the limits of minus n to plus n is kind of understood, I am not going to write that one, just to simplify the equation how it looks. Okay. So, this is what it is, and then you have Bn, Bm complex conjugate. Okay. And here you have minus j 2 pi Fn Tb, here you have a plus Fm Tb, but you can write down this by writing this as n minus m Tb. Okay. Now, do not forget to put the averaging operator. So, if you put the average operation, you are going to put the ensemble average. For what do you mean by ensemble average? Please refer to any of the probability courses that are being conducted. We will unfortunately do not have the time to spend on that one. And you can also show that when you do the averaging, you are actually supposed to put the average on the random variables. These are not random. Okay, this exponential minus j 2 pi f n minus n Tb is not random. So, the randomness comes only from the bit sequence which is random, which we do not know. So, that is the random or the averaging operation that we have put in. There are some mathematical constraints when and how you can interchange the average operation, when you can write down the summation before average operation later, but that is of not really much of a concern to us now. Okay. After this, how to obtain the PST? I have to divide this one by t, which is the total time duration. What is the total time duration? Well, I have transmitted how many pulses? My index n or m goes from minus n to plus n, right, which means there are 2n plus 1 pulses, and therefore, the duration is 2n plus 1 into Tb. Okay. I will remove this, or I can just keep it this way, but of course, n has to go inside. So, I have to pull this limit operator onto the outside of this one. So, I can just do this one, rewrite the whole thing. I will write this as limit of n going to infinity, you have P of f magnitude square divided by 2n plus 1 into Tb. Okay. So, please note that the denominator is increasing. If the numerator has becomes finite and if the denominator keeps on increasing, then the PSD might actually be equal to 0. Let us see whether that would be the case. Now everything else seems to be alright, only thing is how do we evaluate this averaging process, what is the meaning of that? What it means is that at the nth sequence you are looking at Bn, at the mth time slot you are looking at Bm complex conjugate, then you are looking at Bn into Bm complex conjugate, the product, and then you are looking at what is the probability of this particular sequence occurring. Okay. In what possible ways Bn can vary? It can be for the polar form, which let us consider as the first example. Bn can be +1, the sequence at the mth slot can be +1 2, right. You can have +1, here maybe -1, you have -1, you have a +1, and you have -1 and a -1. Okay. The product will be 1, +1, -1, -1 and +1. There are an equal number of +1s and equal number of -1s. If you now assume that all the bits are equally likely, that is to say all bit combinations are equally likely to occur, then this probability would be 1 by 4, 1 by 4, 1 by 4 and 1 by 4. Thus when n is not equal to m, this happens when n is not equal to m of course, then if you multiply the probability with the value, add it next to the probability with the value, probability value and sum it, you are going to get a big 0. Okay. This is the averaging process. What happens when n is equal to m? That is on the nth time slot itself, what can happen? Well, then in that m is equal to n and you are looking at magnitude of Bn square, and then you are trying to average this. If Bn can take on +1, magnitude square will be +1 square, which is +1. If Bn takes on -1, the magnitude square will also be +1 because it is -1 square, right. And if you assume the probability to be equally likely as we have assumed of +1 and -1, this would occur with a probability half, this would occur with a probability half. Therefore, when you add them together, weigh them or find the average value will be equal to 1. Okay. These two conditions can be concisely written as Bn Bm complex conjugate average as delta Nm, where delta Nm is the Kronecker delta function, which would be equal to 1 when n is equal to m, it would be 0 when n is not equal to m. Okay. So for the polar format, this is what we obtain. So you can actually go back and see what is the meaning of that. So here you can replace this Bn Bm complex conjugate by delta Nm. So when you replace that, what you are saying is out of the two summations that you have, one on n and one on m, you choose only those terms where n is equal to m. Throw away all the cases where n is not equal to m. So if you take only those cases where n is equal to m, you are going to get the power spectral density as, so let us call this as power spectral density PSD of f, and this would be equal to limit of n going to infinity P of f magnitude square divided by 2n plus 1 into Tb, and then you have a summation, right, which would be when n is equal to m, that would exist only in that case. So this is the case where n is equal to m, but n is going from -n to +n and there is a 1 here. What happened to the exponential? Well, the exponential vanished. Why did the exponential vanish? Because when n is equal to m, this fellow will be equal to 1. It is the exponential of j into 0, that would be equal to 1. And what is the summation of this one? This is simply 2n plus 1, correct? This is simply 2n plus 1, and therefore PSD that you were looking for is given by, this is for the polar format, okay, is given by P of f magnitude square divided by Tb. In the next module, we are going to look at the meaning of this PSD, as well as we are going to look at what happens to polar RZ format and NRZ format. Thank you very much.